Now that we've seen different types of neural networks and different applications, let's take a look at how we apply them in the real world and explore where they might succeed and where there might still be room for improvement. Looking back at what we've learned in this course, we now know how to apply machine learning to 3 different types of data, or also variations of them. One would be tabular data, where we have numerical or sometimes also categorical variables as our inputs, and we process them with different types of models. One could be, for example, a fully connected neural network or a linear regression model that is just applied to this tabular data. Another type of data could be image data, where we have the image as an input, and we learned that we don't want to apply a fully connected neural network to this, but we want to leverage the inherent structure of image data to our advantage by applying, for example, convolutional neural networks that actually just look at a local window in our input. And finally, we've also seen for sequential data that we would want to apply something like recurrent neural networks or transformer networks that actually leverage the context across the time sequence. One more thing that we want to teach you are residual connections. These are skip connections in our neural network. That means the output of one layer can not only go to the next layer, but we can also skip one layer and add the output of a previous layer to the output of a current layer. And therefore, the information can flow much easier through the network, and also the gradient flows much better. So that makes training easier and allows us to train much deeper models like this ResNet, for example. Now, in addition to the input, we also learned about different types of outputs, where we have, for example, categorical, numerical values, or we have different types of vectorized outputs or sequence outputs that we can now know how to deal with. And they usually determine what kind of task we have and what kind of objective function we need to use. So for categorical, it's obviously classification. For numerical, it's regression. For bounding boxes, this was one of the examples for vectorized regression. Segmentation masks, these are classification tasks where we have a classification for each pixel in the output. And then predicting the next value in a sequence, that can be either a regression or classification task, depending on what type of sequence you have. Labeling a sequence, that would be a classification task, and all of them basically determine what kind of objective we need to use. In addition, they also might sometimes determine what kind of model we want to use. Here, for the example of a segmentation mask prediction, we could apply a RUNet. And that is something where we have in the input the same size as on the output side. And to still manage the computation, we have this downsampling in addition to the convolutional layers that gives us basically a bottleneck where we have a smaller representation of the image and then upsample again to get to the size of the output. And this computation is made much easier by these skip connections from the input side to the output side. Finally, we've now seen what kinds of inputs and outputs we can encounter and how we can deal with them. But in practice, to get the state-of-the-art performance, you often want to just scale the model to the largest you can get if you can afford it. And this is one trend we've seen in the recent years, that a ResNet, which was originally like the first one that beat the state-of-the-art and also the human performance on the ImageNet task, is nowadays outperformed by much larger models that go into the hundreds of millions of parameters. How do we use these models actually? So the models grow in size a lot, but we also, in addition, need to grow our data, because otherwise we cannot really make use of these large models. ImageNet is one example that is rather small by comparison today, with 1.2 million images. And training on this takes a lot of time. But the good thing is we can get a model out of this that is often, when it's trained by researchers in industry or in academia, shared with us. And we can use these models even if we don't have the resources to train it ourselves. Because we can use the pre-trained model that is trained on for a long time on a large data set and do something called transfer learning, where we take the trained model and keep training, continue the training for a short time on a smaller data set, on the data set that we are actually interested in. And that can also be on a small different task. And then we can hope for better performance because these models already, for example, gathered all the information it needs to process images, and we just need to tell it how to identify monkeys in addition to that. And yeah, this is what's called transfer learning, and that is crucial for good performance in small research projects. And with this, can we actually say that deep learning and machine learning is a success nowadays? Well, we outperform humans on very specific tasks, and we have seen many useful applications already in our everyday life, be it speech recognition, self-driving cars, or translation. And with that, maybe it is a success. Maybe we could pop the champagne and just celebrate. But I would put a question mark there because I'm not sure if it's really at that point yet, because there are still a lot of failure points for even the state-of-the-art neural networks. So here you see one example where we try to identify the objects in this image. And here it sees the dragon and identifies it as a bird. And the person in the image is also correctly identified, but the dragon is wrongly identified as a bird. However, this might be the best we could expect from our model because it has never seen a bird in training. And therefore it just predicts a big bird. That might be not too bad. However, let's add some snow to the scene. Suddenly we cannot recognize the dragon anymore, not even as a bird. And that can be problematic, can be even dangerous if we are driving with our self-driving car through this area and we don't see the dragon in front of us. That might get us killed. Finally, if we add even more snow, then we cannot even identify Jon Snow here. So the person is not identified at all, and we might run over him or the dragon. And that is something that is called robustness, and this is something, if we would still be able to classify them correctly, then we would have a robust model. But this is something that neural networks generally struggle a lot with. And even if they perform very well on just normal classification tasks, generalizing to these unnatural, unseen events is hard. Another interesting case where neural networks fail is this example. Here we want to now translate from German to English the sentence die Ärztin und der Pfleger. And it is translated in English to the doctor and the nurse. And that is a correct translation, but there's something interesting going on here because in German we have genders for the different words. We have a female doctor and a male nurse. And in English we don't have these genders, which is fine. But it becomes problematic if we translate into the opposite direction. Now we have the doctor and the nurse in English, and we translate it to der Arzt und die Krankenschwester. Now this is interesting because we have a male doctor and a female nurse. And it is still a valid translation, especially because the system didn't know what genders we wanted to assign, and it needed to assign a gender, so it just picked something arbitrary. But maybe that is not that arbitrary, and it's something that is reflective of the training data that was used. And therefore, this is something that is a bias in our data that can be reflected in the model. And this is something you should be aware of. Because if you don't want to reinforce stereotypes, you might want to address this. And this is something that is not only present in this kind of form, but can be present in any kind of form where you might be biasing your model towards specific things by not having a more balanced data set. So be careful there. Finally, let's answer the question you might be all wondering about now. How can we actually apply deep neural networks in practice? How can we get our hands on this? So first, good news is you don't have to implement everything from scratch. There are deep learning frameworks out there that allow easy development for neural networks, and they have all these operations implemented efficiently as matrix operations. They allow you to easily put your code onto a graphics processing unit, so a graphics card, that makes it much, much faster to train and execute neural networks. And therefore, nowadays we don't use our GPUs anymore for gaming, but we actually use them to train our neural networks on a server. And they also have something called automatic differentiation. So all these tedious derivations that you've seen earlier, they don't need to be performed by you by hand. You can actually just give the model a loss function or a loss value for a given input, parameters, network function, and output, and then it will automatically compute the loss derivative with respect to the parameters. And this is exactly what we need. And the only thing that you actually need to implement yourself, and you can actually use the deep learning frameworks to help you with this, is to implement the network function. Everything else, as soon as you have the data, is performed by the deep learning framework. And which deep learning framework you might want to use is up to you, but we can actually highly recommend PyTorch. This is, of course, based on Python and very flexible, easy to use, good for quick development, very popular in research. That's why we use it as well. And it has an interface that is very close to NumPy and SciPy if you already used to those. TensorFlow is also very flexible. Also, you can implement this in Python, and often it's preferred in some performance critical applications. However, sometimes PyTorch might even be faster than this. So there is a case-to-case basis, but both are completely fine and very well supported in their community and also in the research community. Other deep learning frameworks we don't really can recommend here, because mainly you want to be able to use other people's code and to use models that you might find somewhere in the literature. Just use them, plug and play. In this case, they are usually implemented in either PyTorch or TensorFlow. So if you know any other framework, it might not help you that much, and you might actually get stuck at some point. So learning directly PyTorch or TensorFlow is the best way, we would say. And now let's go to a simple example in PyTorch where we actually show you step by step how you can apply these different methods we talked about before in practice in a small PyTorch example. Now we will see a simple example of how we can implement a short and small neural network model in PyTorch. And this, if you want to follow along, you can just click through the notebook in the same way that I do and try it out for yourself. Okay, let's execute some hidden code, because this is just there for some visualization, and go through the notebook. Our task is the famous MNIST task, which is basically the hello world of the machine learning world. This consists of small images of 28 by 28 pixels of handwritten digits. So these are images of digits that are from 0 to 9 and that are handwritten and in grayscale. So they look like this. So it could be a 7, a 2 or something. And our task, or the task of a neural network, is to predict the correct number based on whatever image is given to the network. And now we first need to execute our dataset function, which downloads the data. So we tell here the system what dataset we want, so that we want the MNIST dataset, the training and the test set, and what kind of transformations we want to do, so some pre-processing so that our neural network knows how to deal with the data. And finally, we put it in some data loaders, which basically walk through the data one mini batch at a time. So we executed this. Your execution might look a bit different. So when it first downloads it for the first time, now that we've defined the data, we arrive at the model. And the model is quite simple. We just have a fully connected network of 2 layers where we have an input size of 784 pixels. So each pixel of our 28 by 28 pixel image is one input to the network. And we have a fully connected network, which is still fine and doable for this small size of our input data. And the output size of our network is 10. So because we have 10 different digits, 0 to 9. Okay, these are the different classes that we want to predict, and we define our model in PyTorch basically exactly in that way, that we tell it, okay, we have 2 layers. The first, the fully connected layer from the input dimension to the hidden dimension. Then we have a sigmoid nonlinearity. We have another linear layer, hidden dimension to out dimension. And then we have a softmax as the final activation that gives us our log probabilities or final output for classification. And in addition to defining how our network looks like, we also need to define how we apply the network function to our inputs. So for a given input, we need to define this forward function where we hand the input to our first layer, then to the sigmoid, then to the fully connected second layer, and then finally to the softmax. And then we return this as the output of our small MNIST model. And then our model, if we look at this, can execute it. It looks exactly like this. So we have linear, sigmoid, linear, and log softmax. And now we can quickly just skip the training and go directly to evaluation. Let's see, with just defining our model, how good our model performs. Note that our model will have randomly initialized weights. So in this case, it will also perform very randomly, and maybe here in this case, mostly just predict 0. And in some cases, 8, 3. This is not a good prediction, of course, and it will always predict wrongly. And the final accuracy is 9.1%. So if you think about that, if you would just guess without having any knowledge of the image, if you would just guess one number every time, you would also achieve an accuracy of around 10% just by chance. So this is exactly what our neural network achieves here, and which is completely fine before we trained it. So now we're getting to the training. And for that, we follow the principle that we actually developed in the course. So here we have we first define a loss function, so an objective. We have an optimizer, which is gradient descent, that performs the updates on our model parameters and has a learning rate. And then we iterate through our training data for multiple epochs, so multiple passes through the entire training data, and for mini batches in each of these iterations. So we always have the input and the expected output from our training data, and with this we get the predictions from our model. Then with these predictions we can compute the loss function against the target output. And finally, we perform a backward computation, which gets us our gradients. And with these gradients, we can take a step into the right direction with the optimizer. And this is our model. We trained this for 5 epochs, so for 5 passes through the training data. And with this, we can now evaluate our model. Let's take a look. And now we are much better. So these numbers here were all predicted correctly, and only one of these 10 numbers, so 10% of our test data, is predicted wrongly. And as you can see here, it's also understandable why this would be the case. So here, this is a very strange 5, right? It's like very curled and like has this loop down here. So it might also be just a 6 that is mislabeled or something, or it is a 5 that is hard to recognize. So the prediction of 6 kind of makes sense, but it's still an error. So the final accuracy is 90%, which means 9 out of 10 images in the test set are accurately predicted. And with this, you can see that our entire process of always defining data, model, and training is basically what we need to rely on also in implementing those concepts. Because we are always following this principle, and these are the things that we need to provide and use our deep neural network framework for to actually implement a machine learning model. Finally, what have we learned about neural networks in the real world? They are often scaled to huge sizes and use a lot of data, but we can actually still use them if we take a pre-trained model and just fine-tune it for whatever application we have. And we don't need to implement everything from scratch. We can use a deep learning framework like PyTorch or TensorFlow to actually do our work. And finally, deep neural networks are not perfect. You should be aware of the many failure cases that there are. Generally, robustness and generalization abilities are problematic, and also you should be aware of biases in your data and whatever can go wrong there.